Welcome to the Thermal Transport Cafe. Speaker says, so today we are very privileged to have Professor Rishi Raj. So all of you know about him. Briefly about him, he joined IIT Patna in 2013 as an assistant professor. Now he's an associate professor in the Department of Mechanical Engineering. He did his BTech in Mechanical Engineering from IIT Guwahati in 2006. And he did his PhD from University of Maryland in 2010. Before he joined in IIT Patna, he was a postdoc in Device Research Lab at MIT. So we are very excited to hear how his team is using sound of boiling for the in-situ prediction and control of boiling regimes. So Dr. Rishi, the floor is yours.
Yeah, thank you, Mohammed. Is my screen visible?
Yes.
Okay. Thanks a lot for the introduction, and I welcome everybody to this talk where I will be focusing on acoustic prediction and control of boiling heat transfer regimes. So we'll primarily be relying on the sound of boiling to accomplish what we typically do using the thermal data. And in this talk, the work is primarily done by Kumar Nishant Ranjan Sinha, Dr. Kumar Nishant Ranjan Sinha, who has also joined the meeting, and he's currently a postdoc with Professor Peter Stefan. Vijay Kumar, who was a master's student and who is doing now PhD with Dr. 𝐀𝐜𝐨𝐿 at UCSB, and I think he has also joined. And Professor Atul Thakur, who is from our department, and he primarily works in the area of mechatronics. So he has been quite helpful in helping us get the control systems. And in this talk, what I will do is quickly introduce the fundamentals. I will not take much time because this community is very well aware of that, and then get to the point, which is how do we intend to use the sound of boiling. So the theme is boiling heat transfer, and it's very clear to all of us that we primarily work towards the Newton's laws of cooling, and the whole idea is to increase the heat transfer coefficient such that we can dissipate a particular amount of heat at very small temperature differences. And in this regard, I don't need to prove to this community that we get the highest possible heat transfer coefficients using the phase change heat transfer such as boiling and condensation. And there are many applications about which also I may not need to brief this community. So let me directly get to the point. And the point is the boiling curve and the boiling regime. So we are very familiar with our typical boiling curve and the heat transfer coefficient curve at the bottom, which is the heat transfer coefficient on the y-axis and the wall superheat on the x-axis. And typically we characterize our boiling regimes as natural convection followed by onset of nucleate boiling, and then the nucleate boiling regime up to the critical heat flux. And beyond the critical heat flux, all of us are very familiar that we have a thermal runaway, and many a times this is not desirable, or in most times it's not desirable because you lose the advantage of the high heat transfer coefficient that we have mentioned in the previous slide, and obviously there are failures due to thermal runaway. And the actual nature of the boiling curve in the transition boiling regime depends on what boundary condition do you imply at the heater surface, whether it's a constant temperature boundary condition, constant heat flux, or something in between, like the case we have where we have a large thermal mass. And most of us are working towards the fact that we want to be in the nucleate boiling regime, and we want to do two things. We want to maximize the heat transfer coefficient that we see in the nucleate boiling regime, as well as we want to extend this limit, the point which is the critical heat flux, so that we can get the advantage of the high heat transfer coefficients up to very high heat flux. And in this regime, primarily, the heat transfer is due to the evolution cycle, which is the cyclic process of bubble nucleation, growth, departure from the heater surface, and reweighting of the heater surface. The same is shown here, where we start with ONB, then we have the evolution cycle, lots of bubbles nucleating, forming on the bubble, departing from the heater surface. There are other events such as coalescence, and this is primarily responsible for giving us the high heat transfer coefficient until we encounter thermal runaway due to critical heat flux, where we primarily have a vapor blanket covering the heater surface. And the fascination with increasing the critical heat flux, figuring out when does it happen, can we predict it, and trying to achieve the high heat transfer coefficients during boiling has kept it still as one of the most relevant topics in the thermal heat transfer. And I just did sometime last year a survey, and we figured out that there are at least 3 Scopus Index publications every day as far as the boiling heat transfer is concerned. And if you want to make a guess as to why that is the situation, you have to look at this plot, which is a nice compilation by 𝐀𝐜𝐿 et al. In Applied Thermal Engineering, where they have just tabulated, where they have just put all the data regarding critical heat flux, or the value of critical heat flux, as well as the wall superheat for boiling on a copper surface, normal polished copper surface with water as the test feed. And what do we see? We see that the heat flux values that have been reported in literature do vary from somewhere around 600 or 500 kilowatts per meter square to even 1600 kilowatts per meter square, or 160 watts per centimeter square. And similarly, the wall superheat varies from somewhere around 12-13 degrees centigrade to maybe 37 degrees centigrade. So this is primarily the reason that we are still so much behind boiling heat transfer. It's very difficult to predict at what heat flux boiling crisis will be observed, and then what is the temperature. And accordingly, and considering the fact that a boiling crisis is an issue, that after that you do not have the control of the thermal transport phenomena, trying to figure out where boiling crisis happens or just delaying is, this has been the state of the art of the research in this field. So if we just try to recap for ourselves why we have so much uncertainty. So all of us attribute it to the fact that boiling is really a multi-scale problem. We have to go from the size of nucleating bubbles to the size of the heater surface, and that can be 3 to 4 orders of magnitude. Boiling is sensitive to a large number of parameters. We obviously have fluid flow, we have heat transfer, then we have multiple phases involved, and that makes it complicated, the whole thermofluidic transport associated with boiling. And it's also very sensitive to practical subtleties. So many times we do experiments in the lab, and if we are not careful with the contamination and other issues, the heat transfer numbers that we get changes significantly. Accordingly, there has been a nice compilation by Professor Mudawar, who showed that if you use these correlations from Zuber correlation or Professor Kandilkar's correlation, which does the correction for the contact angle as well as the inclination, and for that matter, there are other correlations as well. The best match that you can get between the experiments and the predicted heat flux are typically of the order of 40 to 90%, which is very, means we can say the uncertainties are very large. Accordingly, since we are not able to very well characterize the boiling critical heat flux, we don't know, we cannot pinpoint to a heat flux number or a superheat number. The approach has been, let's delay boiling crisis such that we still are sure that we are away from critical heat flux and we can operate in the high heat transfer nucleate boiling regime. So there have been lots of work, and I cannot do justice to cite all of them, but primarily the principle is that you use these very fancy micro nanostructured surfaces, and the idea is that you can improve rewetting and you can have higher critical heat flux as well as the heat transfer coefficient. But the issues are that yes, you are delaying the boiling crisis, but exactly the highest heat transfer coefficient that you typically get is towards the critical heat flux. So you still are not able to operate in that regime because of the associated uncertainties with the value of critical heat flux. And if you are operating a device, maybe during the operation of the device, if there is some sort of contamination, fouling of the heater surface or anything like that, what you thought is a safe limit may not be a safe limit, and hence we have to adopt a very high factor of safety, which primarily implies that we still operate in the low heat transfer coefficient nucleate boiling regime. Just to give a brief overview, there has been a lot of surge in activities, particularly in dealing with machine learning in boiling, and the number of publications that are coming out express that. And much of the work in this field is in using machine learning tools to analyze boiling data better. For example, here is a work from Mosavi et al., where what they have done is they have taken boiling images in various regimes, and then they have trained image recognition algorithm, particularly the convolutional neural network. And what they intend to do is that the algorithm directly tells if there's a new boiling image, whether it is in the nucleate boiling regime or boiling crisis has happened or whatever is the boiling regime. And similarly, there are other works also where people have tried, for example, Su et al. They have looked at boiling images using high-speed camera, trained a network, and the whole idea is to measure or predict bubble parameters. Even Matthew's group has looked into the IR images from the underneath, and the whole idea has been to predict instead of using expensive computational tools to characterize all of the IR data to get back important bubble parameters such as bubble growth time or nucleation site density. They have been able to show that you can use machine learning algorithms and the computational time reduces completely, and these algorithms are very accurate. So this is some of the new trend in this direction, but everybody, the whole idea is we want to understand the boiling mechanism so that we can better predict the critical heat flux as well as the superheat at the critical heat flux, such that in future we can have controls over boiling critical heat flux, and maybe we can deploy other mechanisms so as to minimize thermal runaway. In this regard, the way we look at the problem is obviously through the purview of electronic cooling, but also for larger systems, let's say a typical boiler. Again, at this point of time, I'm not doing flow boiling, but if you look at a typical boiler, you will have these tubes and then the drum. And the issue is really, if you're talking about boiling crisis and you want to pinpoint it, it's very difficult because you may put temperature sensors at a few locations, but the failure may happen somewhere else. Because it's spatio-temporally distributed. We typically will not have access to, while during experimentation, we have access to the bubble images, but in typical experiments, we may not have access to the bubble behavior to predict anything. So we have to still rely either on the thermal data, or we think we can look or we can hear the sound of boiling, and that may give us a lot of information which may otherwise be difficult to obtain in practical application. Why we are interested in the sound of boiling? Because all of us over the years have recognized that it is the bubble behavior which dictate the boiling phenomenon and hence the heat transfer. And the sound of boiling is a direct manifestation of the bubble behavior. So in a way, it imbibes that statistically as well as temporarily resolved information. Another issue with visualization is even if you are able to visualize the boiling behavior, let's imagine you have a circular heater, you are only able to look at the peripheral view of the bubble behavior, and exactly what is happening, let's say at the center of the heater, is not clear to us. However, with the sound, all of those hundreds or thousands of bubbles and how they are oscillating, what is their behavior, sometimes they are coalescing, sometimes they are departing from the heater surface, all of that is obtained in the form of a simple time series signal, for which we have a lot of analysis data. And particularly with the machine learning tools, maybe we can get much more information out, and that's our aim. So I hope you are able to hear the sound that's playing in the background. And here I will give just a brief introduction regarding the sound from bubbles. So whatever we hear, whether it's a raindrop or the roar of a surf, the sound that we hear is primarily due to the formation and collapse of bubbles. And there are many other events such as coalescence and other events, which also contribute in many different ways. Minard, way back in 1993, characterized by doing single bubble experiments that the sound that we hear from bubbles is inversely proportional to their size. So if you have large bubbles, you will have low pitch sound, and vice versa when you have small bubbles. However, this is a very simplified experiment, primarily air bubbles. And we want to translate all of this knowledge for boiling. It's not that we are the first one to speak about sound of boiling. There was a seminal paper published in 1955 in Science by Westwater et al., where they showed that if you plot the heat flux versus the sound of boiling, the axes are reversed here, you can see that the nature of the intensity map of sound, boiling. So this is basically primarily the intensity in decibels, follows a behavior very similar to the boiling curve, where in the nucleate boiling regime, it increases and then peaks, and then the curve reverses. So something like this has been shown. However, there has been a lot of follow-up work after that, and probably due to lack of the analysis tools as well as unavailability of such advanced sensors as we have today, it was primarily concluded that boiling sound is more like a white noise, and hence you cannot get features here. And white noise, for those who are not familiar, means that you will have equal amplitudes at various frequency levels. So it's very difficult to figure out the frequency signature. That was initially concluded. And it was attributed to the fact that there are so many events happening in boiling. There are so many bubbles. You have nucleation, you have cavitation, you have surface popping, you have oscillations, coalescence, that it's very difficult to figure out what is happening there. So we, just based on the experience that our students were doing in the sound, the boiling experiments, and we're able to correlate or predict, even just by listening the sound that CHF is coming or impending, we realized, why don't we really come back to this topic of sound of boiling and try to look at it from a more scientific point of view, now that we have better tools and models. So our experiments are very simple. We basically have a boiling chamber, transparent boiling chamber, where there's a copper block with cartridge heaters. And in the next section of the copper block, which is insulated from all sides using a Teflon, you have these thermocouples, which can give you the heat flux data, as well as you can extrapolate the temperature under steady state conditions to get the wall temperature conditions. We do boiling with pure water. The fluid is typically open to atmosphere. So for all the results that you will see here is the amount of dissolved gas depends on primarily the subcooling we are using. We employ a high-speed camera because we want to do simultaneous audio, visual, as well as thermal characterization. And then we have a hydrophone, which basically through a preamplifier and a DAC, all of the acoustic data is acquired. And in the future, once we have characterized, as you will see in our experiments, what is the behavior of the boiling sound, we also implement and control through a microprocessor, and all those details will be discussed later. So this is primarily our experimental setup. We do experiments on two types of surfaces: simple, plain, polished, machined copper surface. Typically, our heater is roughly around 14 millimeter, 14 millimeter, 14 millimeter in diameter. And we also have nanostructured copper surface of the same size, where this is the typical Grice-like nanostructures, which has been extensively used in boiling. And the purpose here is to understand how does the sound change with these nanostructures. We also vary the boiling fluid. So we have aqueous surfactant solution, for example, sodium dodecyl sulfate, SDS, and we use it at the critical micelle concentration, and similarly aqueous solution of ionic liquid, BMIM-OS, and its concentration again, I think at CMC or half of CMC critical micelle concentration, so below the limit, such that the solution is clear. The methodology is very simple. We vary the input power, which is shown on the y-axis. We maintain it at a particular level. We wait for the temperatures to stabilize to get steady state data, and then we switch on the power to the next level. And we do this at various power levels until we hit thermal runaway, and we can characterize the whole boiling curve like this. We have validated our boiling curves with the data in the literature, and the critical heat flux and the superheat values are reasonable, again, in the whole cloud of the data points that you have seen somewhere in the middle. So we are happy because we don't have any better numbers to benchmark our data with. And then we also do transient experiments, very slow transient experiments. And the idea here is, when you do steady state experiments, you are doing experiments between discrete data points. And right near CHF, either you have data before CHF or after CHF. You really are not able to see what is really happening at CHF. So what is the way? So the way is that we give input to our cartridge heaters and increase that power at a very slow level, such that we can do inverse heat conduction at all points. We can have a continuous boiling curve with data continuously acquired right from the onset of nucleate boiling to critical heat flux and beyond that. So as you would see, this is the power curve. We slowly increase. These experiments are done for more than 2 hours, as you can see. And then when we hit the critical heat flux, initially we have a PID controller set such that the temperature reaches at a particular thermocouple location to a value of 150 degrees centigrade, you switch it off. However, afterwards, we have our machine learning code incorporated to do the same. And then based on the thermal data from the 3 thermocouples, we do inverse heat conduction where we do marching in time and space to back calculate what is our transient heat flux as you see here, and what is our surface temperature data. Here we have the critical heat flux or the thermal runaway, and you can put these two together to plot our boiling curve, which is this whole curve. And as you see, once we reach 150 degrees centigrade, we manually, means there is a control logic, the power is shut down. So there is still some temperature excursion beyond that because of the thermal mass. But after that, the system starts cooling and it goes back to the nucleate boiling regime. On here, I have also plotted the steady state experimental data, which in the nucleate boiling regime, obviously we have only steady state data in the nucleate boiling regime, matches perfectly well with our transient data, both in terms of the heat transfer coefficient as well as the critical heat flux, telling us that, okay, our transient data is reasonable. So I will quickly talk about processing of the acoustic data. So here, during the same experiment duration that you have seen, we are plotting the sound signal, and this is basically in the fluctuations that you see in your hydrophone. And what you have here is onset of nucleate boiling, and then as the boiling is progressing, you have more and more bubbles. The intensity of the sound can be seen to increase. You can further take snippets of sound in any regime. For example, I'm showing here an example of sound in the nucleate boiling regime. We do FFT to see what are the frequency components, and definitely there is a pattern. It's not that it's like a white noise. And then we do this at various heat flux levels right before CHF, and we observe something interesting. Yes, we have a peak similarly at around 200 or 250 hertz that we had in the low nucleate boiling regime, but around 90% CHF, we seem to have another peak emerging at higher frequency values. And then we monitor this sound at these CHF, and as I have told, we have transient data, so we really have the sound at the instance of critical heat flux. And there what we see is now the dominant peak is this second high frequency peak that was emerging late in the nucleate boiling regime. So there are definitely some spectral signatures. And this is just one way of looking at the data, and another way is shown in the left. In the left, you can see intensity versus time. In the right, you can see intensity versus frequency, but we want to see all of them together. So what we do is we take these Fourier transforms in various regimes and put them in the form of what is called a spectrogram, where what you see on the x-axis is the same time. On the y-axis, you have the frequency, and then the color map, which is showing the decibel level, shows the intensity of the sound. So for example, if I look at this red curve, okay, that is manifested here in terms of very high peak in this location. So that is how we have analyzed the sound of boiling, so that we get continuously all of the information from the sound. At any instant, what is the dominant frequency and what is its amplitude? And for that matter, amplitudes at all frequencies. So now what I will do is, in the next slide, I'm going to show you one data for simultaneous thermal, audio, as well as visual characterization of boiling near the boiling crisis. So here is the transient thermal data that you see. So we have the heat flux varying and going up to critical heat flux. Here is the temperature change. Right at CHF, you have temperature excursion. The heat flux comes down. This is the transition boiling regime. Somewhere here we switch off the heater. And so after that, cooling starts and it goes back to the nucleate boiling regime. So there is an increase in the heat flux and the temperature comes down. And we are going to zoom in this particular region, okay, around 20 seconds of data with around 15 seconds of the audio that I will be playing here. And here is the spectrogram that you have seen in the previous slide. And this is the zone we are focusing in. And if I focus in there, we see something characteristic, some change in the frequency behavior that I'm going to play for you. In this video, you will see the bubble behavior switch from mushroom to something else. You will at all points have the values of heat flux and surface temperature. And now that I'm playing it, you will see vertical arrows moving through this point. So I request you to please note what happens when we are at the critical heat flux.
Rishi?
Yes, Professor.
Are you using a pointer? Because
yes,
we can't see anything. Oh, there it is. I see it now. Okay.
Can you see it now?
Yes, thank you.
So I'll just play it 1 second. Sorry for the confusion. I thought my pointer was visible, but now it's visible. So I'll play it once more. So let's see. So now we are moving along this, and you can monitor the heat flux, surface temperature, and you are hearing the sound. So this is right from the just before the critical heat flux to critical heat flux, and then when the stable vapor film forms. And we definitely see a very interesting behavior where we see transition from mushroom-like bubbles to some sort of unstable vapor film and a lot of micro bubbles emanating from that vapor film, which eventually stabilizes into a stable vapor film as seen towards the end. And during this time, when the bubble behavior changes from the mushroom-like bubbles to the micro bubbles emanating from the unstable vapor film, we see this shift in peak frequency, which was also audible to you. While we primarily mostly focused on the pitch of the sound or on the intensity of the sound, but the pitch also changes during this time, wherein it goes from somewhere around 200 to 250 hertz to around 500 hertz or so, the details of which I will show in the next slides. So very clearly, the hypothesis, the comment made earlier that boiling sound is primarily white noise is not clear, and we see very distinct spectral features, and we wanted to further investigate this. In doing so, we said, okay, our previous experiment is near the saturated conditions. Let us also look at the effect of subcooling. So here are the boiling curves at various subcoolings, and we have the same condition that when the heater surface temperature reaches 150 degrees, let's switch off the power supply. And the black curve was the curve that you have seen in the previous slide. And then we increase the subcooling from near saturated 2 degrees centigrade subcooling to 5, 10, 20, 22, 25. And what you see here is that as expected, the critical heat flux increases, but there is a reversal of the boiling curve at higher subcooling values, and that is shown in the zoomed in video here. So we were initially surprised, but when we did some literature survey, we figured out that this is very well mentioned in literature and as micro bubble emission boiling. So when we looked at those literature, we really figured out that the behavior where we are seeing this unstable vapor film and micro bubbles emanating from them is what is referred as to micro bubble emission boiling. However, the issue was people said in literature that MEB is only observed at very high subcoolings, probably beyond 20 degrees centigrade, and it's characterized by the thermal signature where the boiling curve reverses, or you see beyond CHF there is another increase in the heat flux. But we saw this first in the near saturated boiling conditions, the previous experiment that we have shown, and we hear the same sound after CHF, similar to MEB in all our experiments. So we went in further detail, and we, with the intention of trying to figure out why are we really seeing MEB or we are seeing something else. So here is another experiment This is at a very high subcooling of 25 degrees centigrade. We are again near critical heat flux, and we would like to see whether do we get the same sound behavior that we got earlier. And obviously, I have shown you the thermal data for this curve, and you have shown the boiling curve increase or the heat flux increase in the transition boiling regime. So this is typically characterized as MEB, but we want to correlate the change in the sound behavior here with our near saturated experiments earlier. We also have the spectrogram and the raw acoustic data. Here is the power and heat temperature data that you can see here. So this is near CHF, but before. Now this is MEB, what is typically referred to as MEB. And we are moving on this curve. And this continues for a while. This is a very long video. If I can just for a second. So I can play this is for more than 100 seconds, and we have a very stable boiling behavior, and this is the region where we see the heat flux increase. So really, in terms of what is referred to as micro emission, bubble emission boiling, which is MEB, we are actually pointing to that even in our saturated boiling experiments. However, we don't see that reversal of the boiling curve, and in literature also it has been shown that it does not reverse. So is it the reversal of the boiling curve which is primarily MEB, or is it this fundamental bubble behavior and the sound that we are hearing that is MEB? And if that is the case, then what we are saying is that MEB is observed at all subcooling. So we further investigated this topic. We looked at all subcoolings. At all subcoolings, this is 2 degrees, which was our original near saturated boiling data, 10 degrees, 25 degrees subcooling. We monitored what is the frequency behavior, and the frequency behavior is primarily same. You have a low frequency before the critical heat flux, and there is a jump in frequency. But there was a difference. The extent for which you see this behavior, the MEB regime, dependent on what is your subcooling level. So what you have characterized here is the subcooling, then the duration for which we see MEB. Please note that we can also at high subcoolings get very stable behavior, but since we are doing transient experiments, our power is continuously increasing at a slow level. Hence, we cannot see MEB forever even at very high subcooling. But what we realize that the extent of MEB increases with subcooling. The intensity ratios, definitely in all cases, the intensity in the MEB regime is much higher than the intensity in the nucleate boiling regime. And there's also a characteristic shift in peak frequency. However, at what value, from what value to what value does it shift? For example, it shifts from around 220 to 320 at very low subcoolings, while these values change to 450 in the nucleate boiling regime to 880 Hertz in the MEB regime or the transition boiling regime at higher subcooling. So what we were able to figure out here is that probably MEB is observed at all subcoolings. However, that is not reflected in the thermal data because you are doing experiments at discrete conditions. And secondly, the duration is so small in the near saturated or other conditions that you don't get any steady state behavior there. And hence, you only attribute MEB to this reversal of the boiling curve. But the actual bubble behavior, which corresponds to MEB, is observed at all subcoolings. So we further verified this for different types of surfaces. Here is the MEB data for the plain copper surface, and at the bottom you have the MEB data for the nanostructured copper surface. And we saw that nanostructured surface, with everything else remaining the same, in both cases the subcooling is 10 degrees centigrade, provides you much larger extent of the micro emission bubble boiling regime, MEB regime. And again, there is a shift in peak frequency from the low frequency to the high frequency. Actual values of frequency depends on the bubble sizes, which changes with what experiments you are doing and what is the subcooling as well as what is the boiling fluid. But we were getting a hint that if you do anything to delay the formation of stable vapor film, you can increase the extent of MEB. For example, subcooling can do the same. nanostructured surface can allow rewetting of the heater fluid even beyond CHF, and that can delay the formation of the stable vapor film. That also increases the extent of CHF. And the third thing we tried is, obviously, you can also use surfactants, aqueous surfactant solution. Aqueous surfactant solutions lower the surface tension values, and hence the rewetting is easier. And we also saw there that you get much larger extent of MEB, and that extent of MEB also increases as we go from low subcooling to higher subcooling conditions. So with that, we said, finally, let us see what happens when we come back in this cooling curve. So here is an experiment that we are showing at a subcooling of 25 degrees centigrade, where we see really MEB also in the thermal data during the heating pattern, and then we switch off the heater. And during cooling also, we see this multiple peaks in the boiling curve, saying that the same behavior. So once you have a stable vapor film and you are cooling the heater surface, there is this fight between whether the vapor film wants to be stable and unstable. And during this time, there is an unstable vapor film from where microbubbles emanate. And you see that kind of behavior again during quenching experiments. And then it comes back to the normal boiling behavior. So with that, we concluded that there are very definite spectral features of the sound of boiling in various boiling regimes. You can characterize the boiling crisis or critical heat flux with the sound of MEB, micro bubbles that emanate from the heater surface. And there two things happen: the intensity of the sound increases, as well as there is a shift in the peak frequency. And the whole idea was, can you use this peak frequency to detect CHF and arrest thermal runaway? So that was our next work. What we wanted to do was, we wanted to look at this critical heat flux, where we will see that there will be a change in the spectral behavior, which I have already shown earlier. And we want to use this along with a feedback circuit. So what we are doing here is, we are acquiring that sound of boiling. We are monitoring the peak heat flux. And as soon as there is a sudden shift in peak heat flux, we are switching off the power to the heater surface. And we want to see whether this really happens independently in our, autonomously in our experiments. And what we want to notice, how much can we arrest the thermal runaway, which was previously based on just a cutoff when a particular thermocouple temperature or heater surface temperature reached 150 degrees centigrade. So here is the result. So in this experiment, we did transient experiments shown in brown. And as soon as we reached CHF, there was a shift in peak frequency. Our total data acquisition time, because this is live, is roughly around 1 second. And we observed that after 1 second, the system automatically cut off the power. But since we have already had the critical heat flux, and there's a lot of thermal energy stored on the heater surface, and there was a vapor film formation, still we saw some thermal runaway, but it was definitely 30 to 40 degrees centigrade lower than the previous case, and the boiling curve reversed again. So very clearly we were convinced, and I'm only showing the data from one kind of experiment here. We did it on various different types of heaters, and we were always able to arrest the thermal runaway. So it was a success, but not a complete success, because still you are able to only detect critical heat flux. After the damage has happened, you are trying to minimize the extent of the damage, but the eventual aim should be to an advanced prediction of the boiling crisis. And we moved further in that direction. So here what I show you is the peak frequencies in the nucleate boiling regime versus the peak frequencies in the MEB regime for flat copper surface, nanostructured copper surface, and copper surface, but with ionic liquid solution. The previous two ones are with water. And what you would notice is this simple rule-based feedback, that once the frequency exceeds a particular value, switch off the circuit, needs input from the experiment, because where this cutoff frequency has to be set depends on what fluid and heater surface combination you have to use. So it needs some input from experiment and is not very convenient. So can we generalize this approach? And we started moving in that direction. So I will just quickly get to the point. The whole idea would be to shut down the system just before critical heat flux, such that you do not have this thermal runout. And not only that, in future, instead of shutting down the system here, incorporate some additional cooling mechanism such that you can still operate in this high heat transfer coefficient regime without the issue of the thermal runaway. And that's what I will show in next few slides. I will take hardly 5 minutes and then end my talk. So this was the time during March of 2022 when lockdown was imposed all around the world and we were not able to do any further experiments. And then my student came back to me and said, can we actually use some of the machine learning tools in the background of which I have given you earlier? And his inspiration was primarily from a study here, which is based on the characterizing the size of the crowd. And typically the size of the crowd, it was shown here that when only characterized using webcam images is not so accurate. However, if you have a few microphones and you couple it with the sound that you are receiving from the crowd, you can do a very good prediction of what is the size of the crowd, even when it's night, it's a cloudy day. So he simply said, why can't we use the sound of the boiling along with the machine learning tools to predict our boiling regions and eventually go for advanced prediction of boiling prices? To this end, we used a very simple tool which exists in MATLAB and is open for anybody to use. And this is a speech command recognition using deep learning and particularly the convolutional neural network. And the whole idea is you give a lot of training data, 5 seconds audio for different words. For example, here is the audio of yes, and there's maybe 500 such data. Similarly, audio of right, and this is some unknown audio. And the code does is converts this audio into spectrogram and then uses CNN to train a network. And whenever you train a network, you split the whole data set into 80% to 20%. 80% is used for training and 20% is used for validation. So there is around 2000 data points for all of these words, and 20% of that is used for validation. And this code gives a very good prediction in terms of detecting if you speak a new word, it can tell you whether it is from the pool that the network has already been trained or it is some unknown sound. So we simply took this algorithm and said, instead of various words, our sound data in various boiling regimes under steady state conditions, so nucleate boiling or the background, natural convection or the background, nucleate boiling data, and the transition boiling data, these files will be those various categories. For example, we have 2056 sounds in the nucleate boiling regime, which is in the natural convection regime, which is primarily silent, then nucleate boiling a lot of, and only a few data points in the transition boiling regime, because obviously it's not very stable behavior there. And we trained the same network, and we were very happy that we were getting around 99.9% accuracy in terms of prediction. So this whole algorithm seemed to work and is summarized in this video here, where we are doing transient experiments. And what you see here is the temperature and the power input. Power is in the red, and this is the temperature data. Here is the raw audio, and the processed file in terms of spectrogram is shown here. We are moving vertical along this line. Here is the prediction class. The algorithm, just by listening to the sound of boiling, no input from the thermal data, is able to tell that right now you are in the nucleate boiling regime, and when do you go to transition boiling. And here is where we are in the boiling curve. And you will note what happens when we get to critical heat flux. So when we get to critical heat flux, there was a sudden thermal runaway in the boiling curve, and the prediction changed to a new regime, which was transition boiling regime. And then when it comes back to the nucleate boiling regime, it again predicts that. So this was very interesting to us. This was trained on the water data under steady state conditions. We were predicting under the transient conditions. So we said, can we check this on other data without training the network for the new samples? So we did this experiment, and we simply used the network trained on water and pure copper surface to predict the data for nanostructured copper surface, where the CHF value or the wall superheat values are significantly different from our baseline experiment for water. And we got very good predictions. Blue, okay, is the natural convection, where ONB happens more or less matches with our experiments. Then we have continuously nucleate boiling regime, and right at the point where we saw this thermal runaway, we have a prediction for MEB regime or the transition boiling regime. So this was great. We further tested it with aqueous solution of ionic liquids, where the critical heat values are much lower than water and the nanostructured surface, and the heat transfer coefficient is higher, so the same behavior is observed at much lower temperatures. And we were again very successfully able to predict when this behavior is observed, and that was very interesting. What was very interesting was we didn't have any input from the thermal data except for the original training wherein we had given some sound, but that training was also for the baseline case of pure water and flat copper surface. Then we were right away able to resolve one issue. So we used this code to simply cut off our circuit and arrest the thermal runaway. And we didn't have to depend on this rule-based feedback where we had to give the peak frequency at which we should cut off the power once we observe the critical heat flux. So the first issue was solved. However, since in this case also, the code was only telling us that now the system should be shut down after CHF has been obtained. It happened maybe a few 0.5 seconds after the critical heat flux. We still had some thermal runaway very similar to the previous data. So yes, while we were able to do away with the rule-based feedback and we have a general algorithm, we still didn't have an advanced prediction, which we really wanted to get to. So then we really looked at our boiling data and read a lot of literature and tried to identify that very near the critical heat flux, you see this maximum heat transfer coefficient, and after that the heat transfer coefficient starts lowering, and very soon you see this critical heat flux, and this regime is called as departure from nucleate boiling. So we said that this departure from nucleate boiling, can we call it as a new boiling regime? So what we did is we took the nucleate boiling regime data, and it's only for this 3 data points here where the heat transfer curve starts to peak and then the value decreases. We called it named it as a new regime, which is pre-CHF regime, and retrained our network for including a new regime. So now this data point is split in between these 2 regimes, and reran our code on the new training network. And what we saw is very close to critical heat flux, around 97% CHF. Again, this is a different data. This is a transient data. The code was telling that you have a new regime, which is pre-CHF regime. And that is basically some sort of advanced prediction. Yes, when we are running the code, we don't have any input from the thermal data, but you can say that we have taken some input from the thermal boiling curve in terms of defining where this peak is coming and what we can call as the departure from nucleate boiling regime. But still, this was very encouraging. So we then directly applied the control system here, and we were able to see that the code automatically shuts down the power to the system right around 95% CHF values, and you don't have any thermal runaway, which we wanted at the first place, but we were not able to accomplish because in all the other strategies that we have used earlier, it was detection after boiling crisis have happened, while in this case, we were able to completely arrest the thermal runaway. But just to think more practically, the idea in any practical application would not be to shut down the system. Yes, you can shut down the system and this will avoid damage, but can we have some sort of adaptive control or cooling mechanism induced right now when this condition is encountered, such that you can still operate near critical heat flux, even beyond the critical heat flux values in this high heat transfer nucleate boiling regime? So we have some preliminary results here. What you will see here is the temperature and the heat flux values, wherein what we do is we vary the power level in a cyclic manner, even beyond the critical heat flux value, which is shown here. And here is the corresponding audio spectrogram. And since now we have a prediction of the pre-critical heat flux regime, we have told our code that whenever you see that regime, you switch on some jets, which can basically pump water into this big vapor bubble and can avoid thermal runaway. And this is a representative video, not exactly the same video during this experiment because this is a long duration experiment, but it can explain the fundamental concept. So what happens as we are fluctuating above critical heat flux, you can see we can go beyond the critical heat flux value and have an oscillating behavior here without having thermal runaway, since the jet switches on as soon as it sees this pre-critical heat flux behavior. And then I will manually switch off the jet, okay? And when we hit critical heat flux, we have a similar thermal runaway that we have observed earlier. So this is very interesting to us. This is just a thought experiment to show what all we can do now that we have this very beautiful way to predict when critical heat flux is observed without relying on heat transfer numbers. So with that, I will try to summarize my code. So we are using the approach of boiling acoustics in order to predict various boiling regimes and eventually achieve the goal of advanced prediction of critical heat flux. And the whole idea is that you can have a reliable mechanism which can tell you, which can give you the confidence to operate in this high heat transfer coefficient regime near the critical heat flux. And in case you hit that value, you can deploy some sort of adaptive control or cooling mechanism which can still ensure operation in that regime without having thermal runaway. We have some publications on this topic in IGHMT, which is primarily on the detection, simultaneous characterization using audio, visual, and thermal data in experimental thermal and fluid science. I haven't discussed the work on Leidenfrost, but that is in soft matter. And most of the machine learning part that I discussed in published in Shell Reports Physical Science, where we have also uploaded all of our audio data code so that everybody can use it, validate it with their data and baseline and check our approach. So with that, I would like to thank all of you. I think I took 5 to 10 minutes extra, but thank you for listening, and I would be happy to answer any questions you may have.